In the previous sessions, we have looked at factor theorem and fundamental theorem of algebra. Now let's look at conjugate root theorem. Now first, let's look at an example. So we have f sub 2 of x, meaning a quadratic, is equal to x square plus 3x plus 4 is equal to 0. Now let's find the roots using the quadratic formula. So x equal to minus b plus or minus square root of b square minus 4ac divided by 2 times a. And simplifying that, we end up with minus 3 by 2 plus or minus square root of 7 by 2 I. So we have conjugate pair of complex roots. So conjugates are minus 3 by 2 plus root 7 by 2 I and minus 3 by 2 minus root 7 by 2 I. Now, the question that arises is, if a complex root occurs for a polynomial equation of any degree with real coefficients, then is it true that its conjugate also occurs? Now, in case of a quadratic, we can say that because of this plus minus in the quadratic formula. But what about in case of a cubic or a quartic or a quintic equation or any higher degree equations, polynomial equations? So to address that, we look at conjugate root theorem. What it says is that in a polynomial equation with real coefficients, complex roots occur in conjugate pairs. Now, before we actually look at the proof of that, let's look at a property of conjugates that we will require. So we have z is equal to a plus ib. Now what we are going to do is, we are going to take the conjugate of z square, which is written like this with a bar on top and also using a asterisk. Let's substitute z with a plus ib. So we have conjugate of a plus ib square, and let's expand a plus ib square. We get conjugate of a square plus 2aib plus ib square. Now ib square is I square b square. I square is minus 1. So this becomes minus b square. We have conjugate of a square plus 2aib minus b square. Rearranging it, we get conjugate of a square minus b square plus 2aib. Now this again is a complex number where the real part is a square minus b square. So which means now we can take the conjugate. So conjugate is what? Just change the sign of the imaginary part. So we have a square minus b square minus 2aib. This was when we took the conjugate of z square. Now let's look at square of conjugate of z. So here we are interchanging the conjugation and squaring. Square of z conjugate is equal to a minus ib. Conjugate of z is a minus ib, and then we have the square, which is equal to a square minus 2aib plus ib square. Again, because of I square, it becomes minus b square. And we have a square minus b square minus 2aib. So do you notice that this is equal to this? That is the order in which we take the power and the conjugation. Doesn't matter. So using the same argument repeatedly, in general, we can say conjugate of z to the power of m is equal to conjugate of z to the power of m for every positive integer m. So this is one of the properties that we are going to use to prove this theorem. Now let's look at the proof. Let f sub n of x is equal to the polynomial of nth degree is equal to 0, where all coefficients are real. Let z equal to a plus ib be a root. Now, how can we just say that there is a root for this equation, polynomial equation? That is because fundamental theorem of algebra says that nth degree equation will have n number of roots, real or complex, including multiplicity. So which means we are saying let this be one of the roots. Then f sub n of z is equal to 0. That means if we substitute this in this polynomial and simplify it, we will end up with 0. Now taking the complex conjugate on both sides, we get conjugate of f sub n of z is equal to the conjugate of 0, which is equal to 0. So here again we are using another property of conjugates. That is, the conjugate of a real number is itself. Let's take the left hand side. So f sub n of z conjugate is equal to the conjugate of the expanded form of the f sub n of z. Now here we are going to use another property of conjugates, that is conjugation distributes over addition or subtraction. So let me first list down the properties that we are using, properties of conjugates. So we are using the following properties of conjugates. We have the first one, if the coefficients are real, conjugate of a sub k is equal to a sub k. That means the conjugate of a real number is itself. Second property that we are using is just what we saw previously. Conjugate of z to the power of m is equal to conjugate of z to the power of m. And the third property that we are using is complex conjugation distributes over addition and subtraction. Okay, let's proceed. Now, here we are distributing this conjugation over addition. So what happens? A sub naught conjugate times z to the power of n conjugate plus conjugate of a sub 1 times conjugate of z to the power of n minus 2 plus dot 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 till we reach a sub n conjugate. So here we are using property 3, distributes over addition and subtraction. Now we are using the second property and the first property. For real number coefficients, conjugate of those coefficients are the coefficients themselves. So a sub naught conjugate is a sub naught. Similarly, conjugate of a sub 1 is a sub 1. So that those coefficients remain as they are. Now, when it comes to the z to the power of n conjugate, that we can write it as the conjugate of z to the power of n plus a sub 1 times conjugate of z to the power of n minus 1 and so on up to a sub n. So here property 1 and 2 are being used. Now, what does that mean? If you look at the right hand side, that is nothing but a polynomial f sub n of the conjugate of z. And since the left hand side is equal to 0, that means the right hand side is also equal to 0. Hence, because remember, if we are able to reach this statement, that means the conjugate of z is also a root. Hence, if z equal to a plus ib is a root, then its complex conjugate, that is a minus ib, is also a root. So we have proved for any n degree polynomial equation, if a complex number is a root, then its conjugate is also a root. So that was conjugate root theorem. That's it for now. Bye.